On the morning of October 22, 1958, in a fluorescent-lit office on the grounds of Hanscom Air Force Base northwest of Boston, Massachusetts, a 30-year-old electrical engineer named Walter Morrow Jr. sat down to formally commit a proposal to paper that his colleagues at MIT's Lincoln Laboratory had been discussing for several months. Outside, the autumn foliage of eastern Massachusetts had turned gold and crimson, and the base's runways lay under a low, overcast sky. Morrow was not a dramatic man. His colleagues described him as methodical, quietly confident, and possessed of an unusual ability to think through engineering problems in their entirety before committing to a solution. The proposal he was writing that morning was audacious by any standard, and it had grown from a problem that was, at its root, terrifyingly simple. If the Soviet Union decided to start a nuclear war, the United States military might not be able to talk to itself. That concern was the animating anxiety of the American military establishment in the late 1950s. At the height of the Cold War, the United States maintained a vast network of forces deployed across the globe, soldiers and airmen in West Germany, a naval presence spread across both major oceans, command and control centers buried beneath mountains in Colorado, early warning radar installations strung across the Arctic. All of these forces needed to be able to communicate with each other and with the National Command Authority in Washington. Without that communication, the elaborate architecture of deterrence and response that the United States had built at enormous expense over a decade would be, at its most critical moment, mute. American military communications depended on two systems. The first was a network of submarine cables running across the Atlantic and Pacific Ocean floors, connecting the continental United States to overseas bases, fleets, and command centers. These cables had been laid at great cost and carried enormous volumes of traffic. They were, in a practical sense, the nervous system of American global military power. The second was the ionosphere, the layer of charged particles extending from roughly 30 to 600 miles above the Earth's surface, which under normal conditions reflected radio signals across vast distances in the phenomenon called skywave propagation. By bouncing signals off the ionosphere, military radio operators could communicate across thousands of miles without physical cables, maintaining contact with ships at sea, aircraft in flight, and ground forces on multiple continents. Both systems had critical vulnerabilities that military planners understood with increasing clarity as the 1950s progressed. The submarine cables, while difficult to find and difficult to tap, could be cut. Soviet naval forces had both the theoretical capability and, in certain scenarios, the motivation to sever those cables in the opening hours of a conflict. A Soviet submarine operating in the North Atlantic with precise navigation data and the right equipment could, in a matter of hours, isolate American military communications with Europe. The ionosphere was even more unreliable. Solar flares could disrupt it unpredictably. Geomagnetic storms could render it useless for days at a time. And, most troublingly, high-altitude nuclear detonations could destroy its reflective properties entirely. This was not a theoretical concern. In the summer of 1958, the United States military conducted a series of high-altitude nuclear tests called Operation Hardtack, detonating warheads above the Pacific Ocean at altitudes ranging from approximately 17 to 48 miles. The results were alarming in ways that went beyond the test's primary objectives. One detonation in particular, a test called Teak, launched from Johnston Island on July 31, 1958, and detonated at an altitude of approximately 47 miles, produced a blackout of high-frequency radio communications across large portions of the Pacific, lasting as long as 9 hours in Australia and more than 2 hours in Hawaii. The communications disruption was so severe that personnel at the Pentagon grew concerned for hours that Johnston Island itself had been lost. According to Defense Nuclear Agency records, one of the first messages received at the island once communications were restored was simply, "Are you still there?" The Teak test demonstrated, in vivid and unambiguous terms, that a nuclear exchange, or even a series of high-altitude detonations specifically designed to suppress communications rather than destroy targets, could render the ionosphere useless at precisely the moment when communication was most critical. The military needed a communications system that was survivable not just against the physical destruction of ground infrastructure, but against the electromagnetic effects of high-altitude nuclear detonation. The ionosphere, the very medium that made long-range radio communications possible, could be used as a weapon against those communications. The cables that served as a backup to the ionosphere could be cut. The military needed something that was neither a cable nor dependent on the ionosphere. It needed, in effect, a communications system that did not exist. If stories like this, forgotten Cold War experiments with consequences that are still orbiting the Earth today, are the kind of history you want more of, consider subscribing and turning on notifications. Every week, we document cases like this one in full. Now, back to the copper ring. Walter E. Morrow Jr. had been thinking about this problem since joining Lincoln Laboratories' Long-Range Communications Group in 1951. He had arrived at the laboratory shortly after completing his master's degree in electrical engineering at MIT, an institution he had entered in 1945 at the age of 17, after growing up in Springfield, Massachusetts, the son of Walter E. Morrow Sr. His childhood was marked by what biographical accounts describe as an early and intense passion for building things, particularly what he himself called hopeful perpetual motion machines, a phrase that suggests both genuine engineering curiosity and a certain self-aware understanding of the gap between elegant theory and physical reality that would define his career. He received his bachelor's degree in 1949 and his master's in 1951, both in electrical engineering. He joined Lincoln Laboratory that September at the age of 23 and would not leave for more than 4 decades. His early work at the laboratory had included, in 1952, the design of what was probably the world's first transistor flip-flop, a fundamental building block of digital electronics. That contribution illustrated the quality that characterized his engineering throughout his career. He understood the underlying physics of what he was working with well enough to find solutions that were not obvious to his contemporaries. From 1951 onward, Morrow's principal research focus at Lincoln Laboratory was long-range communications, how radio signals propagated through the ionosphere's various layers, how those layers varied with time of day and season, how they responded to different frequencies and transmission geometries. It was intimate, empirical work requiring long hours of observation and careful analysis of propagation data. Over 7 years, he had developed an understanding of the ionosphere's behavior that was probably as comprehensive as any single engineer's in the United States. And out of that understanding had grown a question that was deceptively straightforward. If the natural ionosphere could be disrupted or destroyed by nuclear detonation, was it possible to build an artificial one? The proposal Morrow completed in October 1958 was called Project Needles. Its central concept was breathtaking in its simplicity and staggering in its scale. He proposed placing a permanent ring of copper wire dipole antennas in polar orbit approximately 2,300 miles above the Earth's surface, not a few antennas, and not even a few thousand, but approximately 480 million individual copper needles. Each needle had to be precisely 1.78 centimeters long, exactly half the wavelength of an 8 gigahertz radio signal, and each one thinner than a human hair, with a diameter of roughly 25 micrometers. The total mass of this orbital belt would be between 19 and 28 kilograms, nearly 500 million individual objects, each smaller than a typical household pin, weighing in aggregate less than the average human adult. The engineering rationale was straightforward in concept, if staggering in scale. Copper, when cut to exactly half the wavelength of a radio transmission, acts as a dipole antenna. It absorbs the electromagnetic energy of an incoming signal and re-radiates it, scattering the signal in multiple directions. This is the same principle governing the dipole antennas used in countless terrestrial applications. A sufficiently dense cloud of such dipoles, uniformly distributed in a ring around the planet, would function as a passive reflector, bouncing microwave signals from ground stations on one side of the Earth to receiving stations on the other, with no active electronics, no power source, and no vulnerability to jamming, physical attack, or electromagnetic disruption. Unlike the natural ionosphere, it could not be destroyed by a nuclear detonation above it. Unlike submarine cables, it could not be cut. It would simply be there, orbiting silently, 2,300 miles above every crisis and every conflict. The orbit Morrow specified was deliberately chosen. At 2,300 miles altitude in a polar orbit, passing over both poles rather than following the equator, the belt would gradually precess around the planet under the influence of the Earth's gravitational irregularities, eventually providing coverage across the entire globe. The technical term for this signal-bouncing process is specular scatter, and Morrow had calculated its geometry with precision. The altitudes, frequencies, ground station separations, and antenna sizes the system would need to achieve useful data rates. Morrow's calculations also indicated that solar radiation pressure, the gentle but constant force exerted by photons striking the needle surfaces, would gradually perturb the orbits of individual needles and cause them to spiral downward into the denser atmosphere, where they would burn up within approximately 3 to 5 years. The ring would not be permanent. Each generation of needles would eventually deorbit. But the system would be renewable. If the experiment succeeded, the plan envisioned regularly replenishing the belt through additional launches. The Earth would acquire a technological ring, not unlike Saturn's rings in visual effect, but made of copper and maintained by rocket launches from Vandenberg Air Force Base. The Project Needle's proposal moved through Lincoln Laboratory's internal review process in late 1958 and was forwarded to the Air Force through Department of Defense research channels. Within months, the Air Force had expressed serious interest. The concept directly addressed the communications vulnerability that hardtack had so starkly exposed. Funding was approved, a team of engineers assembled, and the project was given a new name, Project Westford, taken from the town of Westford in northeastern Massachusetts, where the Haystack Observatory maintained a large radio telescope that would monitor and evaluate the needle belt's performance. The project name was 2 words, Westford, while the Massachusetts town itself was 1 word, Westford. Harold Meyer of Ramo Wooldridge contributed to the initial concept alongside Morrow, envisioning the space-based passive reflector as an alternative to the vulnerable ground infrastructure. But Morrow was the primary architect, and the problem of turning the concept into hardware fell to his systems engineering group at Lincoln Laboratory. The engineering challenges were formidable at every stage. The needles had to be manufactured to extraordinary precision. A copper wire, even a millimeter too long or too short, would have its resonant frequency shifted away from the target transmission frequency of 8 gigahertz. rendering it useless as a dipole antenna. The relationship between physical antenna length and operating frequency admits no approximation. Get the length wrong by even a millimeter, and the impedance mismatch between the antenna and the radio signal would prevent any useful energy exchange. Nearly 500 million hair-thin copper wires had to be cut to within fractions of a millimeter of the required length. The manufacturing process Lincoln Laboratory developed involved drawing copper wire to the required diameter, 25 micrometers in the 1961 attempt. Revised to approximately 17.8 micrometers for the 1963 deployment, and then cutting it into precise lengths using an automated chopping machine. The resulting needles were so thin and so light that ordinary air currents in the laboratory could move them. They were barely visible individually, appearing as glints of light rather than as discrete objects. Handling them in bulk required care that bordered on extreme. The needles had to be kept dry, kept from static electricity that would cause them to clump together, and kept away from air currents that would scatter them across the room. And there were, ultimately, somewhere between 480 and 500 million of them. The dispersion mechanism was perhaps the most challenging engineering problem the project faced. The needles, once in orbit, needed to be released gradually and uniformly across the orbital arc rather than all at once, which would have produced a dense local cloud rather than a belt. The solution Morrow's team developed involved embedding the needles in naphthalene, the same organic compound used in traditional mothballs, which would sublimate, transitioning directly from solid to gas without passing through a liquid state when exposed to the vacuum of space. As the naphthalene evaporated in the vacuum and temperature swings of the orbital environment, it would gently release the needles into the surrounding space, ideally spreading them evenly across the orbit. The mechanism was elegant in concept, relying on a straightforward physical property of a common substance to solve a deeply complex engineering problem. It had worked reliably in every ground-based test the team had conducted. The opposition to Project Westford, which had been building since the project became known to the broader scientific community, intensified sharply as the first launch date approached in 1961. What made this controversy significant was not merely that scientists objected to a military program, that was not unusual, but that the objections came from the highest levels of the international scientific community and articulated a principle that had not previously been tested: the right of any single nation to unilaterally alter the near-Earth environment that astronomers worldwide depended on. The International Astronomical Union formally expressed its opposition to the project. Radio astronomers worried that a belt of 480 million metal antennas operating at 8 gigahertz would corrupt their observations of cosmic radio sources. Optical astronomers feared the belt might scatter sunlight in ways that would contaminate their observations of faint objects. These technical concerns were real, though American scientists on the project disputed their severity. But the most significant opposition came from the United Kingdom. Sir Bernard Lovell, the director of the Jodrell Bank Observatory in Cheshire, which had become operational in 1957 with what was then the world's largest steerable radio telescope, a 250-foot parabolic dish, wrote to American scientific authorities expressing concern that transcended the technical details. Lovell's worry was that the American military, without adequate consultation with the international community, was proposing to modify the near-Earth environment that all scientists shared. He wrote about the attitude of mind which makes it possible to undertake such a project without international agreement, suggesting the issue was not the Westford project specifically, but the broader question of who held the right to alter shared environments. Fred Hoyle, the Cambridge University cosmologist known for his research on stellar nucleosynthesis and for a series of influential popular books and broadcasts, was more blunt. He called Project West Ford a major intellectual crime. It was a phrase designed to provoke, and it succeeded, quoted widely in press coverage and becoming shorthand for the scientific community's opposition. The phrase was perhaps excessive, since there was nothing fraudulent about what Morrow and his colleagues were doing, but it captured a genuine moral concern that a military institution had claimed the right to modify a shared environment without consultation, consent, or accountability. The Soviet newspaper Pravda published an article under the headline, "USA Dirties Space." This was obvious propaganda from a state that had its own extensive military space programs and its own disregard for international consultation. But the headline, precisely because it was propaganda, had a certain clarity. It articulated in 4 words the accusation that the more measured language of Western scientists had been building toward. The United States was treating near-Earth space as a resource it owned outright. The issue was raised at the United Nations, where Ambassador Adlai Stevenson, twice the Democratic presidential nominee in 1952 and 1956, and appointed by President Kennedy as his UN representative, defended Project West Ford before the General Assembly. Stevenson argued that the needles were temporary. They would deorbit naturally. The communications capability was important to American national security, and the United States had published its research plans and was prepared to share findings with the scientific community. These arguments were technically accurate, but they did not address the underlying concern, which was not about permanence or publication, but about the principle of unilateral action in a shared environment. Within Lincoln Laboratory, the protests were treated primarily as a bureaucratic obstacle to be managed. The Defense Research Institution's primary obligation was to American national security, and its institutional culture rewarded technical excellence and mission success. The engineers had calculated that interference effects on radio astronomy would be minimal and temporary. The concerns were acknowledged, addressed with technical arguments about the needle's short orbital lifetime, and set aside. The project proceeded. What the technical arguments missed, and what the protests were actually about, was something the engineering culture of the time was not well equipped to process: the concept of shared environment. The near-Earth orbital environment had been, until Sputnik in October 1957, purely theoretical. No one had put anything there. No framework of rights or obligations yet governed it. When Morrow wrote his Project Needles proposal in 1958, there was no institutional architecture, no legal framework, and no established diplomatic norm that would have required him to consider whether any nation had the right to place 480 million pieces of copper in orbit. From a legal standpoint, it was simply not prohibited. Lovell understood that this legal vacuum was the real problem. His letter to American scientific authorities was not primarily about the West Ford needles. It was about the broader principle that the absence of a legal prohibition does not mean an action is without consequence for others, and that the international scientific community was a stakeholder in decisions about near-Earth space that had a legitimate claim to be consulted. That argument, that shared environments require shared governance, was one that the American defense establishment of the early 1960s was not prepared to accept. The practical arguments were on the American side. The principle was on Lovell's side. History has vindicated the principle. On October 21, 1961, the first operational test payload launched from Vandenberg Air Force Base in California aboard an Atlas Agena rocket. The payload, designated Westford 1, carried the needle dispenser alongside a Midas 4 early warning satellite as a piggyback payload. The launch was successful. The rocket performed normally, the payload separated as planned, and Westford 1 achieved the intended orbit. Ground controllers at the Haystack Observatory and at the Millstone Hill Observatory transmitted the radio command to activate the dispersion mechanism. Nothing happened as intended. The naphthalene sublimation system, which had worked reliably in every ground-based test, failed to perform correctly in the actual space environment. The vacuum was present. The temperature cycling was present. But the naphthalene did not sublimate uniformly as the models had predicted. Instead, it evaporated unevenly, and the differential evaporation caused the needle package to behave in ways that ground testing had not anticipated. Rather than releasing the copper wires gradually into a uniform cloud, the dispenser produced 4 or 5 distinct clumps of tangled copper wire that deployed into orbit without dispersing further. The clumps floated uselessly around the planet at the intended altitude, reflecting nothing, communicating nothing, serving only as evidence that the difference between a ground test and an actual space deployment was larger than the engineering team had fully appreciated. 4 clumps. After years of development, millions of dollars in engineering costs, and a significant expenditure of political capital defending the project against international protest, the first operational test of Project Westford had produced 4 metallic clusters and a demonstration that space is considerably harder than it looks from a laboratory in Massachusetts. The failure was scientifically valuable in the way failures often are. It provided data that success would not have provided. The Lincoln Laboratory team spent the following 2 years analyzing the performance of the naphthalene dispersion system in detail, developing revised thermal and mechanical models of how the package had behaved in orbit, and redesigning the dispenser to address the failure modes the 1961 test had identified. The packaging geometry, the naphthalene matrix density, and the spin rate of the deployment mechanism were all substantially revised. The new design incorporated a mechanism that spun the dispenser at 6 to 8 revolutions per second during deployment, providing centrifugal force to help separate individual needles from the evaporating naphthalene matrix. Ground testing of the revised design was extensive, with particular attention to approximating the thermal conditions the package would experience in orbit. Meanwhile, the 4 clumps from the failed 1961 deployment were still orbiting the Earth. The same solar radiation pressure that was designed to deorbit individual needles within 3 to 5 years acted on clumped masses much more slowly. The ratio of surface area to mass for a clump was far less favorable than for individual needles, making the solar pressure force proportionally weaker. The clumps would be up there for decades. They are still there. By the spring of 1963, the redesigned system was ready. The second test payload was assembled at Hanscom Air Force Base with a care that reflected both the engineers' desire to succeed and their acute awareness of the scrutiny the project was under. Morrow, leading the system's engineering group, bore direct responsibility for the outcome. The payload was mounted as a piggyback on the Midas 6 satellite, alongside Dash 1 and several smaller experimental satellites. On the morning of May 9, 1963, an Atlas rocket lifted from Vandenberg Air Force Base. The launch window had been chosen to place the payload in a polar orbit at an inclination of 87 degrees, which would cause the needle belt to achieve near-global coverage as the orbit gradually precessed under the influence of the Earth's irregular gravitational field. The rocket performed as expected. The payload separated and achieved the intended orbit at approximately 3,600 kilometers altitude. The radio command was sent. The dispersion mechanism activated, the needles began to spread. Within hours, instruments at the Haystack Observatory and at the Millstone Hill Observatory detected the signature of the dispersing copper cloud. Over the following days, tracking data confirmed that the needles were spreading across the orbital arc as designed, gradually thinning from a dense cloud into a more diffuse belt. The distribution was not perfectly uniform. Some regions were denser than others, and some naphthalene had again failed to sublimate completely, producing localized clumps alongside the dispersed needles. But enough of the payload had deployed correctly to allow the communications tests that were the project's primary objective. The first successful voice transmission through the Westford Needle Belt took place within days of the launch. Engineers at Camp Park's tracking station in Pleasanton, California aimed a 60-foot parabolic dish antenna at the portion of the sky where the belt was passing overhead and transmitted a signal at 8 gigahertz, the frequency the needles had been cut to resonate at. The signal traveled upward through approximately 3,600 kilometers of near vacuum, encountered the belt of copper dipoles scattered in multiple directions, and a portion of it continued toward the eastern United States. At the Millstone Hill Observatory in Massachusetts, a similarly large receiving antenna collected the scattered signal. The two stations, more than 2,800 miles apart, had exchanged a voice transmission via a cloud of copper needles orbiting above them. The data rate achieved was 20 kilobits per second. Modest compared to what a submarine cable could carry, but sufficient for real-time voice communication and for teletype transmissions. By any technical measure, Project Westford had worked. The physics Morrow had proposed in his 1958 paper was validated. The engineering, after the 1961 failure and the subsequent redesign, had proven capable of deploying the system as designed. An MIT Outstanding Achievement Award citation would later describe the achievement as an imaginative contribution to a new concept of intercontinental microwave communication. Walter Morrow, 35 years old in the spring of 1963, had done what he set out to do, but even before the Westford belt degraded, which it did as the individual needles deorbited on schedule over the following months, it had become clear that Project Westford was technologically obsolete. The reason was Telstar 1. AT&T had launched Telstar 1 from Cape Canaveral on July 10, 1962, while the Lincoln Laboratory team was still redesigning the failed 1961 dispersion mechanism and preparing for the second launch. Telstar was an active relay satellite containing electronics that received incoming signals, amplified them, and retransmitted them on a different frequency. It was roughly spherical, about 34 inches across, and covered in 3,600 solar cells that powered its electronics. The day after its launch, on July 11, 1962, Telstar relayed its first television pictures, a non-public test transmission of a flag outside the Andover, Maine ground station, received at Plumeur-Bodou in France. Nearly 2 weeks later, on July 23rd, it carried the first publicly broadcast live transatlantic television signal featuring the Statue of Liberty, the Eiffel Tower, and remarks by President Kennedy. It was, by any measure, a demonstration of what satellite communications could become. Even before Telstar, NASA's Echo 1, a 100-foot aluminized balloon launched in 1960, had already demonstrated the passive reflector concept in a simpler form, showing that the idea of bouncing signals off orbiting objects was already attracting competition and attention. But Telstar was in a different category entirely. Within weeks of its first broadcasts, it had demonstrated that a single active satellite could carry multiple simultaneous voice and data channels across the Atlantic with far greater fidelity, far greater capacity, and far simpler ground equipment than Project Westford required. Where Westford needed massive 60-foot parabolic dish antennas and precise orbital timing to achieve 20 kilobits per second, Telstar needed only modest ground equipment and provided multiple simultaneous channels. The fundamental technical difference was decisive. Passive reflectors like the Westford needles were inherently limited by the physics governing how electromagnetic energy scatters off small resonant objects. Even a belt of 480 million perfectly deployed copper dipoles could only reflect a small fraction of the energy that hit it in any particular direction. Active satellites amplified the signal electronically, meaning even a small satellite with modest power could relay more useful signal than a cloud of passive reflectors orders of magnitude larger. As transistors and microelectronics continued to improve at the rates that would later be formalized as Moore's law, active satellites would only become more capable and less expensive. Passive reflectors would not improve. The physics of scattering was fixed. Military planners concluded by the summer of 1963 that continued investment in a passive reflector system could not be justified when active satellites offered superior performance in every meaningful dimension. The survivability argument that a diffuse cloud of copper needles could not be targeted and destroyed, while active satellites had merit in principle, but was outweighed by the enormous practical limitations of the passive system. The massive ground antennas, the restricted frequencies, the limited bandwidth. Project Westford was cancelled before the end of 1963, not because it had failed. The 1963 deployment had been a genuine success, but because it had succeeded at demonstrating a capability that was immediately superseded by superior technology. Lincoln Laboratory's own post-project assessment acknowledged this with characteristic precision. The project had been an undeniable success technically, but had little impact in terms of operational employment. It worked, and it didn't matter. For Walter Morrow, the outcome was a particular kind of professional experience, the kind where the physics is right and the context has moved on. His engineering was sound, his concept was valid. His execution, after the 1961 failure and subsequent redesign, had been successful, but the world had advanced past him while he was working. He was 35 years old when the project ended, with decades of career ahead of him, and he would go on to significantly greater achievements. But in the autumn of 1963, he had built a ring of copper around the Earth that nobody needed. The needle belt from the 1963 deployment dispersed and deorbited over the following years, largely as designed. Individual needles that had successfully separated from the naphthalene matrix were affected by solar radiation pressure as predicted and gradually spiraled back into the atmosphere, burning up harmlessly as they descended. Most of the dispersed needles were gone within 3 to 5 years, but the clumps, the sections where naphthalene had failed to sublimate completely, leaving wads of tangled copper wire rather than individual dispersed needles, were a different matter. These aggregates, with their unfavorable surface area-to-mass ratios, were largely immune to the solar pressure mechanism designed to remove them. They remained at 3,600 kilometers altitude, diminishing gradually as the Earth's residual atmospheric drag slowly robbed them of velocity over years and decades. Added to those clumps were the 4 from the failed 1961 Westford 1 mission, which had been orbiting all along. By the late 1960s, the near-Earth orbital environment contained somewhere between 8 and a dozen distinct clumps of Westford copper wire, occupying altitudes that would later become heavily trafficked orbital regimes. By the 1990s, as the space debris problem had become a recognized concern in the space operations community, the Westford clumps were among the documented debris objects tracked by military and civilian space surveillance systems. By the mid-2000s, the number of clumps larger than 10 centimeters that could be reliably tracked stood at 44. As of April 2023, it was still 44. The clumps remain. 44 clumps of copper wire, each roughly the size of a tennis ball or smaller, orbiting the Earth at 3,600 kilometers altitude, left there by a military communications experiment conducted 60 years ago in the service of a strategic problem that no longer exists. The Cold War ended in 1991. The Soviet Union dissolved. The submarine cables that Westford was designed to replace now carry the overwhelming majority of the world's internet traffic, having evolved from copper to fiber optic lines capable of carrying petabits per second, far beyond anything the engineers of 1958 could have imagined. Active communications satellites have become so numerous and so capable that the Westford concept, even if it had worked perfectly, and continued to work, would have been a historical footnote rather than an operational system. There is a particular irony in MIT Lincoln Laboratory's relationship to those clumps. Beginning in 1989, the laboratory, under the leadership of Walter Morrow, who had been appointed its director in 1977, began operating high-powered radar systems designed to track and catalog the growing cloud of debris in Earth orbit. The Millstone Hill Observatory in Massachusetts, the same facility where the Westford communications tests had been conducted in 1963, became one of the primary instruments for tracking orbital debris. The Westford needle clumps are among the objects its systems monitor. The laboratory that put them there now watches them, using technology that did not exist when the needles were launched, performing a kind of decades-delayed environmental accounting for decisions made under Morrow's own technical leadership a quarter-century earlier. It would be a clean moral narrative if Morrow had spent his directorship haunted by the debris he had created in his youth. The available record does not support that interpretation. He was a practical man who had worked on dozens of programs over a long career, and Project Westford was one of many projects. The laboratory's tracking of orbital debris was a practical response to a real and growing problem, not an act of institutional penance. Morrow directed the laboratory through 21 years that included air traffic control systems, advanced radar technology, ballistic missile defense research, and early work on biological and chemical defense. He served on the Defense Science Board for 22 years. He was married for 65 years to Janice Lombard Morrow. He died in February 2017 at the age of 88. The legacy of Project Westford cannot be reduced to the copper clumps still in orbit, or to the technical success followed by immediate obsolescence, or to the institutional irony of the laboratory that created the debris now tracking it. The project's most significant legacy may be in the domain of international space law and the governance of the orbital environment, a domain that did not exist as such in 1958 and that Project Westford helped inadvertently to bring into being. The protests generated by Project Westford established for the first time a framework of international concern about the unilateral modification of the near-Earth environment. The specific objections varied. Some were about radio interference, some about optical pollution, some about orbital debris, some about the principle of acting without consultation. But the collective effect was to force a recognition at the level of international diplomacy that the space environment was a shared resource with stakeholders beyond the nation that happened to have the rocket technology to act there. Adlai Stevenson's defense of West Ford before the United Nations General Assembly, whatever its merits in the specific case, established an implicit acknowledgement that such actions were subject to international scrutiny. The United States had been compelled to send its ambassador to the UN to explain why it had placed 480 million copper needles in orbit. That represented in miniature the beginning of a principle that would eventually be formalized, that nations using outer space had obligations to the international community, not merely rights. The Outer Space Treaty of 1967, which established the foundational framework of international space law and has been signed by most spacefaring nations, included provisions going considerably beyond prohibitions on nuclear weapons in space and national claims of sovereignty. Among those provisions was language recognizing that parties should conduct activities in outer space with due regard to the corresponding interests of all other states parties to the treaty, and establishing mechanisms for consultation when planned activities would cause potentially harmful interference. The West Ford controversy had helped establish the conceptual territory that made such provisions plausible. Lovell's concern about the attitude of mind which makes it possible without international agreement had found, a decade later, a partial institutional response. That legacy has grown rather than diminished in the decades since. The Kessler syndrome, a scenario described by NASA scientist Donald Kessler in a 1978 paper co-authored with Burton Coeur-Palais, gave formal mathematical expression to a concern that the West Ford controversy had raised in intuitive terms 15 years earlier. Kessler and Coeur-Palais demonstrated that above a certain threshold of debris density, collisions between orbiting objects would generate additional debris, which would in turn cause additional collisions in a cascade that could eventually render certain orbital altitudes unusable. The West Ford clumps contributed a small amount to this density, but more importantly, the West Ford controversy had established, long before Kessler's formal analysis, that objects placed in orbit without attention to their long-term behavior constituted a real and lasting cost to the shared orbital environment. SpaceX's Starlink constellation, which had deployed more than 7,000 satellites by early 2026, with plans for tens of thousands more, generated protests from astronomers that echoed the protests against Project West Ford more than 60 years earlier. The brightness of Starlink satellites in the night sky and their interference with astronomical observations became a focus of international debate. The International Astronomical Union, the same body that had formally opposed Project West Ford in 1961, issued statements of concern about large satellite constellations. Individual astronomers wrote public letters. The specific language was different, the institutional context was different, but the underlying concern was recognizably the same, that a powerful entity was proposing to modify the shared space environment in ways that affected everyone's access to the sky without adequate consultation or international agreement. Fred Hoyle's characterization of Project West Ford as a major intellectual crime was excessive as applied to that specific project because the Lincoln Laboratory engineers were acting in good faith on a genuine military problem, with technology they had reason to believe would deorbit naturally and harmlessly. But Hoyle's underlying point, that there are obligations attached to actions in shared environments, and that ignoring those obligations constitutes a form of moral failure regardless of the legitimacy of the proximate goal, has proved prescient. The history of the orbital environment since 1963 is in significant part a history of such failures, accumulated by many actors across many nations, each acting on legitimate proximate goals, each contributing to a cumulative problem that no single actor fully anticipated or intended. Walter Morrow was 30 years old when he wrote Project Needles in the autumn of 1958, proposing to wrap the Earth in copper to solve a problem he understood with extraordinary technical precision. He was 35 when the needles went up and the transmissions worked. He was 88 when he died in February 2017, having led Lincoln Laboratory for 21 years, having received every significant award his field offered, having watched the Cold War end and the Soviet Union dissolve, and the communications satellite industry become one of the most consequential technological revolutions in human history. 4 of those clumps from the 1961 failure were still in orbit the day he died. 44 total remain tracked and catalogued today. They are not a threat to human life. They pose a small but non-trivial collision risk to operating satellites. They will continue to deorbit slowly as the thin upper atmosphere gradually drains their orbital energy over the coming decades. Some may last another generation. They are evidence of a decision made in 1958 to solve a problem that was real, with an approach that was creative, in a context that was genuinely dangerous, without adequate consideration of what would happen to the things put in orbit that did not come back down as planned. The distance between what an idea looks like on paper, the elegant physics of copper dipoles at half-wavelength resonance, the neat geometrical diagrams of ground stations and orbital belts, the calculated trajectory of solar radiation pressure gently returning each needle to the atmosphere, and what it looks like in practice, 60 years later, in the form of 44 clumps of tangled copper wire orbiting the Earth at 600 kilometers altitude through an environment that has become the foundational infrastructure of global telecommunications, is not a measure of bad faith or incompetence. It is a measure of the limits of what any engineer can see from a laboratory in Massachusetts in 1958, looking up at a sky that was still, by any reasonable measure, empty. The problem Morrow was trying to solve was real and serious, and remained serious for decades. The solution he proposed was ingenious and, within its own terms, successful. The consequence, the debris that remains, was not a failure of his solution, but a failure of the broader context in which it was deployed, a context that did not yet have the conceptual vocabulary, the institutional mechanisms, or the accumulated experience to think carefully about what it meant to put things in orbit that did not come down. That vocabulary, those mechanisms, and that experience have since been developed, imperfectly, incompletely, but genuinely, partly in response to Project Westford and the controversy it generated. The Outer Space Treaty exists in part because the Westford protests established that space was a shared environment whose modification required international consultation. The orbital debris tracking programs exist, in part, because the Westford clumps helped establish that what goes up does not always come down on schedule. The current debates about satellite constellations exist, in part, because the astronomical community's objections to Westford established that the clarity of the sky was a resource worth defending. It is a thin and incomplete legacy for 480 million copper needles and 60 years. But it is a legacy, and it is real, and it is continuing. The 44 clumps are still up there, each one a small, spinning, silent reminder of the distance between what we can imagine and what we can see coming.